Hello and welcome to the homework helper video for section 5.2. We're finally getting there. We're finally getting to a place where we can solve this area under the curve problem, the second main problem in calculus. I do want you to keep in mind that if you think back to chapter 3, we introduced derivatives with that limit definition, right? And that was kind of tedious. There's a lot of algebra and limits involved. It took some time. But then later on we learned some shortcuts for taking derivatives. You know, we learned the power rule, we learned the quotient rule, all those nice little shortcuts. And that's going to happen here as well. So this is the more tedious way. This is the sort of the derivation of the methods that we use. And then there's going to be an easier way, some shortcuts later on. So just keep that in mind. We're going to struggle through this limit definition, and then we'll find some easier ways to do these problems in a little while later on in the chapter. But what we're doing here is we're using the limit process to find the area under a curve, and the limit that we use for that is the limit as n approaches infinity of the sum of all these rectangles from I equals 1 to n of f of c sub I times delta x. So don't forget what we're doing. So moving over to the graph over here. Remember what we're doing in this process is we're starting on the first interval and we're creating a rectangle, right? And we're going to create all these rectangles to approximate the area under the curve, right? So we're going to have a whole bunch of rectangles. And we're going to sum the area. We're going to find the area of all those rectangles, right? That's what delta x stands and f of ci stands for. Delta x it's the change in x for each rectangle, so that represents the width of each of these rectangles. And f of c sub I is supposed to represent the height of each one of the rectangles as we move along. So f of c sub I times delta x is the area of each rectangle, and we're summing all of those areas together. They're going to be n. N is going to stand for the number of rectangles, right? And then we're going to take the number of rectangles to infinity. So we're going to have infinitely many small, little, tiny, infinitesimally wide rectangles, and we're going to add up all those areas together. That's sort of the idea, okay? So just keep that in mind as we're going along. All we're really doing here is, in a very fancy way, is we're adding up a whole bunch of rectangles, infinitely many of them, in fact. I'm actually going to make this process a little bit easier. I'm going to do this problem from 0 to 2. Because of the symmetry of this graph, we don't have to go from -2 to 2. We could just go from 0 to 2 and get that area, the area of this region, right, half of it, and then multiply that answer by 2. So I'm going to change the interval here from 0 to 2. And in the end, remember to multiply my answer by 2. Okay? So, here we go. The first thing we want to figure out is delta x. That's where we want to start. Delta x stands for the width of each one of these rectangles. So, if you think about the fact that we're starting from 0 and going to 2, the idea of the formula is we're going to call that, in general, they call that a and b. So we're starting at a and going to b. If I want to figure out the width of that entire interval, I would do b minus a. And if there are n rectangles, n is the number of rectangles, then each rectangle will have a width of b minus a, the entire width, right, divided by n, the number of rectangles. So that's the formula for delta x. It's b minus a divided by n. So in this case, the interval ends at 2, so it's 2, and it started at 0, so 2 minus 0, all divided by n. So our formula for the width of each rectangle is just going to be 2 over n. That's delta x, okay? The next thing we want to figure out is a little formula for c sub I. Keep in mind that I is keeping track of our summation. In other words, it's keeping track of what rectangle we're on, right? So I is 1, then I is 2, then I is 3, all the way up to n, however many rectangles we want. And so c sub I is going to keep track of, it's going to be an x value, right? And it's going to keep track of which little subinterval we're on. So we're going to do a right endpoint method where the rectangles are, the height of each rectangle is derived from the right endpoint. And this first one, if you think about it, will be at a plus 1 width. And then the next one, this next x value, will be at a plus 2 widths. And then the next one will be a plus 3 widths, etc. So our formula for c sub I is going to be a plus the width times whichever rectangle we're on, which is what I keeps track of, right? So our little formula for all these x values, c sub I, is going to be the starting point plus however many widths we need to get to that actual x value, okay? So given that our a value in this case is 0, we just figured out delta x is 2 over n times I. So just 2 over n times I. Okay? So that's our little formula for the x values. Well, the only reason to get the x values is that so we can put them into the function to get how high that rectangle will actually be, right? Get the height of each rectangle, right? We're going to plug in c sub 1 and get that into the function, and that will give me the height at c sub 1, right? So we need to figure out a formula for f of c sub I. So all this means, keep in mind, this is just function notation. What it means is plug our expression for c sub I in, which was c sub I is 2 over n times I, in to the original function, right? So it's 4 minus x squared is our original function. So I'm just going to do 4 minus c sub I, 2 over ni, right, squared. Right? So that's my nice little formula for that. Just simplifying that a little bit, I'm going to square this term, right? So 4 minus 2 squared is 4, n squared, I squared. So that's a little formula for the height at each one of our x values. All right? Given that we have n rectangles, and I is just counting which sub-rectangle, which rectangle we're on, right? All right, good. So now I can fill out my limit. The limit that we want to calculate is the limit as n approaches infinity of the sum of I equals 1 to n of f of ci, which is 4 minus 4 over n squared I squared, times our delta x, which is 2 over n. So we're summing all of that together. Okay, so the first thing we're going to do, we're going to kind of work our way inside out. I'm going to simplify this expression, then calculate the sum, and then perform the limit as n goes to infinity, which will actually be the easiest part. That last part, once we've simplified all this stuff, taking the limit is probably the easiest part of this entire process. Anyway, so first simplifying, I'm going to just distribute the 2 over n to both of these terms in here. So that will be 8 over n. Right, 4 times 2 over n is 8 over n, minus 4 over n squared I squared times 2 over n is 8 over n cubed I squared. So this is the expression that I want to take the sum of. Sum I equals 1 to n, and I want to do the limit of that as n goes to infinity. Okay, great. Let me scroll down a little bit. This is where these summation formulas that you've been studying in this section come in. Okay, so I've only listed 3 of them here, but these are the 3 that I'm going to have you use. There's also, well, there's formulas for all of them. I to the 4th, I to the 5th, but there's also one listed for I cubed in the textbook. I won't have you use that one very much. We'll just go up to I squared for our purposes, okay? So these are the 3 we're going to use, and in this case, the I squared is pretty self-explanatory. What you do is you replace the I squared in this expression with this formula, right? With the formula for n, right? So that one's pretty self-explanatory. For 8 over n, keep in mind that as far as the sum is concerned, 8 over n is a constant, right? What's changing every time in the sum is I, right? I changes from 1, then 2, then 3, then 4, all the way up to n. But there's no I in this term. So this is a constant term as far as the sum is concerned. So when I am calculating the sum of this, when I put 1 into this term, it'll just be over 8 over n. And when I plug in 2, it'll be 8 over n again. And it'll just keep being 8 over n every time. And there will be n of those. In other words, you treat it like this constant, c. All you're going to do is say, oh, it's 8 over n times n, because 8 over n is a constant as far as the sum is concerned. So I'm just going to put 8 over n times n here, because that's what the formula here tells me to do. For the I squared, 8 over n cubed, again, is just a constant as far as the sum is concerned, so I can take that out of the sum, and then I squared has a nice formula down here. Now, the way the formula is written in the textbook is with things like this, and this is how most people write them. It's not the textbook's fault. This is how most people write these rules. What I've written over here for you is a simplified version, an expanded version of that. So in other words, if you multiplied all this out in the numerator and then split all the terms you get up over 6 for each term, this is what that would simplify to. I just find that this form of the formula is easier because otherwise you'd have to do this expansion and split up the individual terms every time you do one of these limits, and the limits are complicated enough without having to do that. So I like to use this, and I actually think that this is easier to remember. N cubed over 3 plus n squared over 2 plus n over 6, I think that's easier to remember than all of this over here, okay? And something similar for I, when you're summing this rule, when you're summing these up for I. When you use this summation formula, it's much easier, I think, to use this form of it right here, okay? All right, so when we replace the I squared, the point here is, when I replace that I squared, I'm going to replace it with this right here. It's n cubed over 3 plus n squared over 2 plus n over 6. Now, once you use those formulas to get rid of, to replace the i's, or there's no I in this term, but once you do that summation formula, you don't need the summation notation anymore. We have done the sum. So now I'm just going to write out here the limit as n approaches infinity. Okay? Great. We're getting there. We're really close. I'm just going to simplify the inside of this and then do the limit as n goes to infinity. So I've got the limit as n goes to infinity. Of course, 8 over n times n is just 8 minus, I'm just distributing here, right? I'm going to distribute this negative 8 over n cubed, right? So 8 over n cubed times this is just going to, the n cubes are going to cancel out, right? And I'll just get 8 over 3. And when I multiply this by the next term, well, I'll have an n left in the denominator, right? It'll be negative because it's a negative 8 over n cubed times this. There'll be 1 n left in the denominator, and 2 goes into 8 4 times. So it'll be n in the denominator and 4 in the numerator, right? And then for the last term, plus, let's see, the 8 and the 6, that will reduce to 4 over 3, right? And I've got an n in the numerator and an n cubed in the denominator, so that'll be n squared in the denominator. Okay. So now we're just going to do the limit of this expression. Yeah? So keep in mind that when you do this limit, 4 over n, for example, is just going to go to 0, right? If n goes to infinity, we've learned that this goes to 0 because the denominator is going to increase without bound. So it's going to be 4 divided by some very, very large number, and that's just going to go to 0. Same thing for this term. Because of that n squared in the denominator, this term just goes to 0. So all I'm left with, and I've just done the limit, so I don't need the limit notation anymore, but all I'm left with is 8 minus 8 over 3. Right? Oh, I just got to figure out what 8 minus 8 over 3 is. 24 over 3 minus, it's 16 over 3. Don't forget that in the very beginning, I simplified the problem by making it go from 0 to 2. And so instead of doing this entire region here for the graph, I just started from 0 to 2. So I do have to multiply my answer by 2, because 16 over 3 is just the area of half of what I'm interested in. So I'm going to multiply that by 2. Of course, that's 32 divided by 3. Okay? That is the hard way. That's the long way, the limit process for finding the area under the curve. I hope all of that makes sense. I hope that helps with the homework a little bit. It's an involved process. I think you can scroll back up here and say, yeah, that kind of looks fancy. Look at all these nice fun symbols we're using. But when you really break down what all those symbols stand for, it's actually not that complicated. Please email me if you have any questions about that. Please email me if you have any questions about anything else in the class. And keep moving forward.